Okay, today we're going to finish up chapter 2. Our objective is we want to be able to assess the normality of a distribution, okay? Which means we want to decide if we're given a data set, is that data set approximately normal or not? All right, we'll talk later about what it could be if it's not. Today we're just saying, is it normal or is it not normal? All right, so there are two methods you can use. Method number one is you can graph it. You can use a frequency histogram or a stem plot to determine if the graph is approximately bell-shaped and symmetric. You want to look at the data. The other thing you want to do is you want to compare the count of observations in each interval with the empirical rule. All right. And then method number two, we'll talk about after we do an example of method number one. So method number one, what we're going to do is we're going to take this data set. All right. The measurements below describe the usable capacity in cubic feet, how big the inside is of a refrigerator. It's a sample of 36 side-by-side fridges. So are the data close to normal? You will notice, hopefully, that I already put them in ascending order for you, just to make it a little easier when you count them. You're going to come over to your calculator. I've got them in here. I typed them all in. I called it capacity. So what method number one said to do was it said to create a histogram or a stem plot. You could also look at a dot plot. You can add to your notes or a dot plot, that's fine. So if we just make a new page, data and statistics capacity, yeah, I'd say that's a pretty decent graph. Keep in mind that like these, the first one belongs down here. It's just that they get like stacked, they float sometimes because the pixels, they can't fit them, which is where making a histogram is nice. That's approximately normal. It's not perfect, but it's looking not bad. Okay, it's definitely bell-shaped. It's looking pretty symmetric. This is a little higher than this, but it's off by 2. It's not too bad. So then the next thing you want to do, all right, is the other part of method number one is you need to check to see how well your data goes with the empirical rule. The percentages for empirical rule are 68%, 95%, 99.7% for 1, 2, and 3 standard deviations, respectively. So if we go back to our notes, I already kind of wrote this out. All right, my mean is 15.83. My standard deviation is 1.22. Keep in mind, you get that by doing menu, stats, stat calculations, one variable statistics. Here's my mean. All right. And oops, I scrolled way too far, sorry. And here's my sample standard deviation, S. Sample, because in the problem, it tells us it's a sample of 36 refrigerators. So I actually made a mistake. I wrote sigma, but I really should have used S for sample standard deviation. So I used the number sample standard deviation, but I should have put the S for 1.22 instead of sigma. So I'm checking, is it at least, all right? Is at least 68% of the data of these data points, is at least 68% between my mean plus or minus 1 standard deviation. So 15.83 minus 1.2 puts me here. 15.83 plus 1.22 puts me here. And then I count. How many of these numbers lie in between these? Be careful. Don't count 14.6. It's outside to the left. Okay. Don't count 17. Yes, count 17.0, but don't count 17.2. So as you add them up, right, there are 24 out of 36 that fit in, which is 66.7% of your data points. Okay, which is pretty close. Not bad. Approximate. We're going is it approximately normal? All right. Because you see the question, are the data close to normal? Then I say, all right, now I'm going to go 2 standard deviations. Take my mean, subtract 1.2, subtract 1.2, go 2 to the left, and then add it, go 2 to the right. How many fall in this window? And I get 34 out of 36, or 94.4%. Okay, so that's good. We expected 95. We got 94.4%. It's pretty great. Okay. If we go a 3rd standard deviation, subtract 1 more, add 1 more. All right. If you look here, right, this actually covers every single number, 36 out of 36. So it's 100%. That's why I wrote these are at least 68%, at least 95%, at least 99.7%. So I didn't write down my final answer, but my final answer would be, yes, it appears as though this distribution is approximately normal. First, the histogram appears to be approximately normal with no skewness or outliers. Also, when I check my empirical rule, the percentages are extremely close to what we expect them to be using the empirical rule. Okay. Now, method number 2 is a totally different way of doing it. You can construct a normal probability plot. What a normal probability plot is when you're going to graph, they actually convert every single data point to a z-score. Okay, so there are 36 refrigerators. They're going to make a scatter plot where the x-axis are your original values and the y-axis are your z-scores. You'll see. You would never, ever do this by hand. I would never in a million years expect you to do 36 z-scores and then graph all 36 z-scores. That's just cruel and unusual, right? So instead what you can do is come back to your histogram. If you hit Control Menu, just like we've been doing to change it from a box plot to a histogram to a dot plot and all that, you've never noticed, but they actually have a normal probability plot as a choice. So just as you hit Control Menu to get here, you're going to pick normal probability plot. Here are our x's. Here are our expected z-scores. So they did all 36 z-scores. Notice it's z equals x minus mu over standard deviation. If the normal probability plot shows up in a line, that means that your original data was normal. Okay, so I'll say it again. If your normal probability plot is linear, then that is strong evidence that your original data was approximately normal, right? Which I wrote here as method number 2. Construct a normal probability plot. If your data distribution is close to normal, then the plotted points in your normal probability plot will lie close to a straight line. So you could write for method number 2, after constructing a normal probability plot, you do a quick sketch, okay? You could say, since the normal probability plot is linear, then the original data is approximately normal. And you could just stop there. So if you like the normal probability plot, you could use that method. If you like this method of counting up how many and matching it to the empirical rule, that's also perfectly valid. You would only do this if the question says something like, are the data close to normal? Or assess the normality of the data, all right? Is the data normal? That's the only time you need to do this. So if we take a look, we could also, sometimes they give it to you. They don't give you the data set, so you can't plug them in and do it on your own, but they already gave us the histogram and they gave us the normal probability plot. Okay, they called it a normal quartile plot, which is fine. It's the same idea as a normal probability plot. So if you look at the histogram, this is definitely not normal. This is right skewed severely with outliers. If you look at the normal probability plot, this is absolutely curved, right? So it is not linear. So my answer was, looking at the histogram and the normal probability plot, NPP is a common abbreviation for normal probability plot. The distribution of areas for the 50 states is not normal. The histogram is right skewed with an outlier, and the normal probability plot is not linear, indicating the original data is not linear, right? I bet this is Alaska. Okay, and this is probably what, California, Texas, and then here's all the other states. We have lots of small states space-wise, and then we have just very few that are enormous states. Okay, and that's it. All right, and here are some really good problems to practice to make sure you are good to go. We've got some more z-score practice and then some normal practice.